Steve, it's all yours. Let me go ahead, grab the screen, and I'll get out of your way. Thank you.
Thanks, Harold. Okay, so my background is not a physicist. I assembled this presentation for my networking buddies, my classical networking buddies, who are very curious about how the issues associated with quantum networking. And so this presentation is oriented much more towards classical networking, trying to explain the issues associated with doing, if you decide that if you want to do quantum networking. Devices done a bunch of networking companies. The slide you're looking at is a map of the internet, all the BGP autonomous systems, which is all the sort of conglomeration of networks within the autonomous systems. And there's a website you can go to where you can fly around into this beast, have a look at it. So to start, I'm going to talk a little bit about sort of the classical applications of networking and how they evolved. Some of the emerging quantum applications, why there are wrinkles, and what some of the problems and issues are and the wrinkles in doing quantum networking, and how we can solve them, what's in our toolbox to fix that. And just to reveal the secret, it has a lot to do with entanglement and teleportation, which I'll talk about. And I'll talk a little bit about architecture and designs. And this is the architecture and device designs are a moving target, and they're being updated constantly. And finally, at the end of this, I'd like to talk about something that I'm interested in, which is entangled management, and to talk about how entanglement management and how that relates to quantum networking. And I think that's a really fascinating subject. So basically, I think the lesson for over the years is applications drive networks. The basic set of applications drove the initial set of networking. The advances in technology then in turn iterated onto to generate next generation networking. You had faster devices, you had optical encoding techniques that provided better bandwidth, inexpensive laser technologies, new materials, processors, tools for building ASICs to build next generation networking applications. And as I sit here and zoom out all over this to you, the fact that we have adequate bandwidth to be able to deliver this. And as far as I can tell, my Dropbox folder is just to refresh as I use these terms. I'm going to use the terms of routers and switches, and talk about addressing. Classical routing is forwarding, packets moving around with IPv4 and v6 addresses. For routing, you have how to figure out paths to connect boxes together, how you distribute routes, for example, using BGP. But at the bottom of this, and there's a sort of a classic modern router architecture on the right, the secret of networking really is that all you're really doing is copying some data in memory in one machine to another machine in another location. And I think I've reduced a solid, $100 billion business to a single secret there. But that's what networking really is. So if you buy my premise that applications drive networks, here's some of the emerging quantum applications. Certainly you have encryption, and there's some interesting protocols for doing encryption. In particular, the fact that you can generate mediation. Quantum sensing is emerging, that is quantum devices that measure quantum fields that can then in turn be distributed. That information can be distributed back to a central processing. There's a central processor for analysis, and I have an example for that. And we have distributed quantum computing, that is being able to assemble larger quantum systems from smaller quantum systems. And in that particular case, you may want to think of the networking not so much as networking as it's an interconnect. There's applications for doing telescopes, interferometers. You have Amazon bracket on the bottom right for doing cloud computing. There's measurements, and there's synchronized clocks, and there's new uses coming out for supporting sort of distributed quantum computing. Here's an example of some magnetometry devices for doing quantum. In particular, how would you deploy quantum sensors on a fault line for doing earthquake detection? And if you had a sensor on the fault lines, how would you then in turn transmit the quantum information to a cloud computer, quantum cloud computer, for doing, for example, fast Fourier analysis to figure out whether you have shocks, low frequency movement in that Earth's surface. So that's it. And I talked briefly about this, which is building. How do you build large quantum systems out of smaller quantum systems? And in this particular case, again, I said it was an interconnect problem. But I think that whether I say interconnect or network, it's the same problem. And how do you basically build machines that can support factor, for example, RSA, or do quantum chemistry on large machines? So people are building networks. ESNet is building one to connect to DOE labs. There's one being worked on in Delft, the University of Delft, connecting in Amsterdam and across the EU. And there's one actually in Boston that connects MIT and Harvard and BBN. And the interesting part is the white line that's in this picture goes right over my house, just so that you know how connected I am. So what's the problem here? And the problem here is, how do you send a qubit of information from one end to another? And, what's the difference between a qubit and a bit? And, fundamentally, if it was a bit, it's easy to forward this across the network. But a qubit has some strange characteristics that require a certain amount of careful handling. So what's a qubit? I think that if you've been coming to these lectures, you probably know, but essentially it encodes an amplitude of values, and that it's composed of, it's a superposition of two basis states, where in particular the A and B are complex numbers, points on a Bloch sphere, in which the amplitudes add up to 1 squared. And when you measure this, you get a probability of A squared, you'll get 0. And when you measure, you'll get a 1 with a probability of B squared. Again, my job, or the original presentation, was to present this to classical networking folks. And my intuition that I asked them to all think about was that a qubit encodes a probability distribution, and that it's not a 1 or a 0, but a probability distribution that when you measure it, a much more interesting way to talk about what a qubit is. Qubits show up in a lot of different spaces and a lot of different modalities. Photons, trapped ions, you have transmons, you have semiconductor spins, you have cold atoms. All of these are different physical representations of qubits. And this will become important because some modalities of physical modalities of qubits are more interesting than others when we do quantum networking. So how do we do this? How do we reliably transfer our qubits through this quantum network? And by reliable, how do we not incur errors? And physical qubits will decohere with noise. How do you prevent that? What's the best path for transferring the qubits? Once upon a time, the internet was just a point-to-point link. Now we have a network. How do we figure out the best path for moving one qubit through a switch or a repeater to another switch or repeater to our final destination? And I think more interestingly, what quantum mechanic restrictions constrain our engineering approaches. And in particular, as I mentioned before about modalities, we have potentially spin atom qubits, which may be used to measure magnetic fields, and we need to convert them to polarization photons to transmit over a fiber optic link. So we have this problem of transduction, and how do we manage that? What kind of devices? What kind of errors does that incur in making that happen? That conversion, the transduction. Here's which is a problem that any qubit, anything we do in quantum networking must obey quantum mechanics. Okay, we can't clone qubits. That is, we can't make copies. We can't measure it. We can only perform quantum mechanical operations on the qubits, and that we do have some interesting tricks we can do. For example, though we can't make a direct copy of a qubit, we can swap them. We can swap values. That's a valid quantum mechanical operation. So number two here is I think the most significant one is that you can't make copies of qubits. And if you remember the secret that I talked about earlier, copying which is copying the fact that we're just copying data and memory from one machine to another, that's classical networking defined. But there is no quantum mechanical operation to copy qubits, okay? Well, another reason is that it's hard to do classical error correction because you can't necessarily copy the state of the classic. You can't copy the state of a qubit multiple times to reduce the number of errors. We'll come back to that. And it's a pretty easy proof to show that there's no quantum mechanical operation. It's a couple of lines to do that. And I think fundamentally that at the quantum mechanical level, you can't create new information. That is, you can move it around, but you can't create new information. And this is a serious engineering problem. And somewhere I read, which I've forgotten, is that the implication of qubit cloning is that I can do faster than light communication. I forget the justification of that, but somewhere. So the other problem I have is with comparing classical networking and quantum networking is I can't measure it. So I can't amplify it because the amplification is a measurement. The qubit here is sensitive and noise sensitive. And so I need to be careful about isolating the qubits, keeping them away from a variety of different types of noise, ranging from optical fiber issues, etc. And of course, measurements in this particular space are irreversible. That is, once I've done the measurement or I've changed it, you cannot get it back. So we need to engineering constraint, no copying, and I can't amplify it to do that. So I briefly talked about this, which is the transduction, which is the fact that I'm going to store my sensor, using that as an example application, is maybe implemented as a trapped ion or a colored diamond. But in order for me to transmit it, I need to convert it to a photon. And not only do I need to convert it to a photon, I need to convert it to telecom wavelengths for optical transmissions. And that's approximately correct, but that's the so, and more problems. As I transmit a photon on an optical link, I have a bunch of problems. Optical loss. I may have splices in here that introduce noise. A variety. I need to also be careful, since I can't do amplification, that my placement of whatever I put in the middle of here, repeaters, is sensitive, or that distance is sensitive to optical loss. And finally, there's noise. And, you know, any model that has noise with e to the minus whatever it is not a great model. And so what you see here is that without error correction, and you have the distance here and the time and the encoding techniques, you lose your quantum. You lose your you fail to have you can't recover from the errors. So there's from one end to another. So let's talk about some of the solutions. So I think one of the classical folks all wanted to transfer a bit, and it's not. It's a quantum mechanical problem. That is, all the devices that I use in here need to obey quantum mechanics, no matter what they are. Transduction issues or memory issues or optical links, they all have to obey quantum networking. I cannot leave, in order to do this, I cannot leave the quantum domain to make this all work, to transfer one qubit from the other. And so the implication of this is that all the networking devices are small quantum computers. They need to support a couple of 1 and 2 gate systems. They potentially have some storage, and they need to do transduction. But they're all small quantum computers. So as much as we think that the classic system where you have an end system and a switch or a router in the middle, these are all different flavors of quantum computers. However, as I think I've painted myself into a box here into making this difficult, there are some quantum mechanical tools that we can use to make this work. And I'm not going to, and the tools we can use are entanglement, we can use teleportation. Again, no cloning, but I can do swapping. In the most simplistic case, I can use optical networking and optical devices to provide some of the mechanisms that I require for doing networking. I'm going to skip over error correcting codes, but there are techniques for managing the errors by entangling more qubits and doing purification, doing measurements on that. So the distillation and purification allows me to create stronger qubits from more weaker qubits. That's a whole 1-hour talk unto itself. So I don't really want to get into explaining entanglement because basically I fail. But there is no classic analog for entanglement. But entanglement will be our tool that we'll use for quantum networking. And basically, the 2 qubits, when entangled, have correlated results when measured. And they have some other interesting characteristics. And we'll talk about that. But again, I don't want to get too detailed into what entanglement is. However, simplistically, the quantum entangled bell pairs and a certain type of entangled set of qubits can be used for teleportation. And the way to think about these entanglement pairs is that they're one-time bandwidth, they're one-time use for bandwidth reservation. And that's a really bad analogy, classic analogy, but I think it's as close as I can come to describe it. The key thing here is one time, because we're going to come back to that. The next example here is the always additionally mysterious quantum mechanical tool, which is teleportation. And teleportation is a way in which we can transfer quantum information from one location to another. And there's protocols to do that. And it uses, it's a simple protocol, which I'm, again, not going to describe, but it requires classical communication to make it to work. And to not violate the superluminal issues of communication to do that. And the important thing is that this is not This is transferring the value of the qubit from one spot to another, or that probability distribution that I talked about from one qubit to another. It's not anything else other than that particular value. And so that's another tool that we're going to use. Teleportation relies on entanglement. And so we're going to use, teleportation will be sort of our mechanism for transporting our quantum information. So as I said before, our final sort of piece of all this is that we can do swapping. That is, it doesn't create or destroy information, quantum information, and it is a valid quantum mechanical operation. And what we're going to use is these particular three things: swapping, teleportation, and entanglement as our basis for doing quantum networking. And here's an example of a very simple quantum swap here at the bottom of a quantum circuit to show you that's simple. So as I said, quantum tools, entanglement, teleportation, and swapping. And I want to stop and ask if anyone has any questions here, because this is a good place to stop.
I don't see any in the chat. Anybody?
Okay.
I do have one. I've got one quick statement.
Sure.
You said entangled bell pairs, one-time use bandwidth reservation. What do you mean by that? What is that?
When you do teleportation, you need a bell pair for teleportation, and when you do teleportation, you will destroy the bell pair to do that. And so that's the idea here, is that you can entangle a set of qubits and put one, create an entangled set of qubits and put one in a box in your closet and send one up to the International Space Station, and they will remain entangled. And you can then use those two entangled qubits for teleportation. But once you do use that, they're no longer entangled and you can't use them anymore. So it's a one-time resource use. Make sense? Okay.
I think so, yep.
Okay, so how are we going to do this? Well, we're going to build first thing we're going to do is we need to have an optical path, and we need to build a high fidelity quantum capable optical path. And in particular, the repeaters of the devices we're going to use in the middle of this need to be located in such a distance to not incur too much optic. So we're going to build these intermediate systems, which I'm going to call a quantum repeater, which I've already told you is a small quantum computer. And our end systems here are going to entangle a storage qubit, for example, from a quantum sensor that's a magnetometer. It's going to entangle a storage qubit with a flying qubit. It's a photon. And that particular technology, there's a variety of different technologies floating around to be able to do that. But that's called transduction to make that all work. But anything that you can do to entangle a storage qubit with a flying qubit. And at the bottom here, we have a end system, which is doing our transduction, our optical links in the middle, and our destination end system at the other side. So a sensor at one end and potentially a quantum cloud computer at the other end to process that. And so how are we going to do this? So we have our physical link here. So what we're going to do is we're going to do something called entanglement swapping, which is the merging of the technology, the three tools that I talked about before, the entanglement, the teleportation, and the swapping. And so what we're going to do is perform hop-by-hop entanglement through our repeaters. And we're going to swap and entangle the entanglements using our quantum repeaters. And eventually, through this swapping, we're going to have entanglement between our two end nodes. And once we have our entanglement between our two end nodes, we're going to use teleportation transfer the quantum information. And again, it's a one-time use once we have the entanglement. And I have a slide to show that. So what's a quantum repeater? A quantum repeater needs to be able to support entanglement over a distance. It needs to be able to do error management. Potentially needs to store qubits, though there's some designs where you don't need to do that. And it is a minimal functional quantum computer. From an engineering point of view, it needs a classic control system. It needs like all quantum computers, there's a classic control system to make this all work, to synchronize the entanglement, to indicate whether entanglement has occurred, etc. And the optical quantum repeaters, you can use optical beam splitters to make this to do entanglement. And I'm not going to spend a lot of time going through that, but you can satisfy yourself about the math. In this particular example, this is a trapped ion system, which is easily the transduction between trapped ions and photons is really straightforward here. And in this particular case, they make for really good end systems if you're building quantum networking. So I'm going to just talk a little bit about this in the sense that one of the techniques for building quantum repeaters is to use optics to do that and to use beam splitters to make this all happen. And there's using both a beam splitter and a polarized beam splitter, you can convince yourself that photons arriving right here, you have photon A coming in here and photon B coming in there. And remember, I described earlier how the spin atom or the storage qubit is transduced with a photon. In this particular case, A is already entangled with a spin atom qubit on an end system here. So you're looking at two photons arriving that are already entangled, and your goal here is to entangle the entanglement for doing that. And so you can use polarized beam splitters to do this. And you can convince yourself, you can convince yourself that in fact, as you go through and do this, that you can put this all together. And here's a quick example of a photon coming in on the A side that's entangled, and how the beam splitters make this work and work through the detectors here. I'm going to skip over the details for this. And you can do the math to figure out how this all works, and there's a surprising result of the entanglement in which the photons will come out of the same, randomly exit out of the same port. Good math problem for you. And as I said, I've gone through the beam splitters. I now am going to put them in a polarized beam splitter, and when they go through a polarized beam splitter, they will be swapped and entangled, and the detection of those particular photons will herald the fact that the original two spin atoms at either end are now entangled. Okay, so what I've done is I've started out with an atom pair and a photon, and an atom and photon pair at either end. I've passed them through this optical system, and I've now measured the photons and destroyed the photons, but the two spin atom qubits at either end are now entangled. So they're now entangled, though they've never been in physical contact with each other, which is pretty sort of amazing. So let's put this all together here. And so I've showed you how to do entanglement swapping between the end system with the destruction of photons here. So here's sort of the diagrammatic way of putting this. So we have my end systems and repeaters. So the first thing, the little icon, the triangular icon in the middle, is my beam splitters. So the first thing I'm going to do is do entanglement between my end system and repeater. My repeater is going to generate a photon, and it's going to entangle a spin atom inside a repeater. I'm going to do this 3 times. After that sequence has happened, and as it's synchronized by a control system, I'm now going to entangle the entanglement. So if you look on the left, can now entangle the spin atoms that are stored in repeaters. And then the third sequence of this is that I can now complete the entanglement of the entanglement to get the 2 end systems entangled as my Bell pair. And finally, after that, I can do my teleportation to move that entanglement that I'm using, transduction to move photons and atoms, legitimate quantum mechanical operations, and teleportation to move the information from one end to another. All completely, all quantum mechanical operations as implemented by a bunch of different devices, a bunch of different sort of physical instantiations of quantum devices, beam splitters, transduction, etc. So that's what we've done. So we've moved a qubit back between quantum devices, and the secret answer is that we teleport the qubit from the destination, from the source to the destination. So there are other technologies for doing this, but clearly there's photons in the middle here. There's other new repeater technologies that come out. There's single photon devices, repeaters. There's a variety of different ways of transmitting photons between repeaters that are emerging. And so that even when the first time I did this slide a year ago, excuse me, there's new technologies that have come out that have better, that are more applicable, that have better error management to do that. And I think if you look at the splitters, you can see that I have a kind of a narrow window. And so people have addressed this by looking at other techniques for transmitting photons, entangled photons, without necessarily having the tight requirements, the tight timing requirements that the optical technology has. So just for fun, I described all of this as a bunch of as a set of devices, physical devices. In a way, it's a quantum mechanical operation here, and this is a circuit diagram that just shows you what this looks like on a simple quantum computer. And on the left here, I'm entangling, I'm creating 2 Bell pairs. Those are the 2 red boxes here. And that's the idea here, is that's simulating a transduction between a spin atom and a photon. The qubit that I want to transmit is at the upper left here. That's what I'm going to teleport. The middle blue box is where I'm doing my swaps and measures. And so that's when I've completed the blue box, qubits here for my Bell pair that I'm going to use for teleportation. The third red box is my Bell state measurement. Sorry, mislabeled that. My Bell state measurement for teleportation. And then finally, the last box on the right is my recovery mechanism from the qubit on the upper left. So I've kind of described a physical implementation of a pretty straightforward quantum circuit that will run on a quantum computer. And I had this running on a simulator just to convince myself about the technology. The swaps can be done in a variety of different ways, optically, for doing, rather than optics to do this. There's cavity. It's a variety of technologies to do that. There's mostly single qubits, single photons that are entangled and sent through other cavities that are also entangled at the other end. And so these are emerging technologies, emerging devices that people are experimenting with. So just as I kind of move on here, there's the review here, because I'd like to talk about some of the things that I find interesting from a networking point of view. So just to do this, we did hop-by-hop entanglement using swapping here. And then ultimately we ended up with end-system entanglement. And we did teleportation of the actual qubit for in any of these systems has to obey the laws of quantum mechanics. So that's sort of the basic, how do I forward a qubit from one end to another sort of story here. So I've kind of hustled through that here, and I want to stop and ask if people have questions.
Any questions out there?
I would like to ask a question. This is Anis Rahman from Harrisburg. And in your slide, so this is, I'm trying to just learn. You had that in the transportation module or the diagram, you had that spin, then you had the photons, and you had another spin. So spin is obviously an electronic property, and photons are photons. So what kind of photons we are talking here? Thank you.
So are you referring to this picture?
Yes.
Okay. So this is a technology. This is the transduction technology I talked about, which is the idea that you can use a variety of different materials and approaches to entangle a spin photon or a colored defect in a diamond with a photon, and excite that with a laser to generate, in one particular case, to generate a photon to make that all work. I'm not a materials person, and so the materials, how this actually works is best left to a there are technologies for doing this. In fact, I have a paper in front of me that talks about how you do transduction between the different tools to make this work. So that it's a it's a complicated physics problem to generate to be able to entangle the photons and the spin. In terms of what types of photons, actually the way this needs to work is, especially in the optical space with the beam splitters, is that they are indistinguishable photons from anything else. And in fact, when they reach the beam splitters, they have to be quantum mechanically, the beam splitters cannot know, they have to be indistinguishable for the entanglement to happen. So I'm not quite sure what you mean by what kinds of photons.
Or meaning the wavelength of the photons. So
okay. So actually, I glossed over this. The photons that may get generated on transduction can be wavelength converted down to telecom. And it turns out that, much to my surprise, that's not a measurement. And so that whatever wavelength that you generated at that, and it's possible that the technology will generate them at UV, you can do wavelength conversion with a NZI to down to telecom. Other questions?
Yes, I have a question.
Sure.
This is Tamer. I often come to the New York meetup.
Hi, Tamer.
My question is, so how much of this has been realized? And specifically, one thing I'm always wondering when I here about this topic is you need, part of this is that you need memory, quantum memory, and quantum states decohere. So I'm wondering whether the state of the art right now for having a quantum state, can we have a quantum state that lasts long enough for communication to happen?
Well, that is some excellent questions, outstanding questions. So what I presented actually was the optical beam splitter. And the reason, and I kind of like glossed a little bit over this, but the optical beam splitter doesn't necessarily require memory to work, but it only works for single hop, so that you can, so the dumb version of this version of this is you have an end system that's connected by a single repeater, an optical repeater, that will perform the entanglement and the swap with no memory to do that. As soon as you add other hops in here, you do need memory to make this all work. And then you get into what I was talking about before, that these repeater devices look like small quantum computers. They have qubits. They have qubits that they need to do storage, and you need to do transduction to do that. Now, the issue that you're talking about, which is the decoherence in these repeaters, is an interesting problem in that, there are error correction techniques for maintaining or sustaining the fidelity over some period of time. But you also have this problem is that as you're going through and doing this element swapping in routers or in switches, you need to make sure that you don't, those intermediate quantum memories don't decohere. It's possible that decohere in this, okay? So that it's possible that you've gone through this elaborate swapping protocol, quantum swapping protocol, and that one of the qubits has decohered and you've lost your entanglement to do this, and you don't know. And so you're going to do your teleportation operation, and it's going to go into the vacuum to make this work. Okay, so I want to talk about that a little bit when I kind of move on. The implementation, people have built the beam splitter repeaters here for doing the memoryless repeaters. There are devices that exist at the other end of Cambridge in labs at MIT where people have built devices that do have quantum memories, simple quantum memories that last for some period of time, but not a lot, not particularly long enough to be able to do multiple hops to do that. They decohere too quickly. But I think from a pure networking point of view, I sort of feel that's a materials problem. How do you provide better isolation? Is it a better materials? Can I build better materials to make this work? Can I build better control systems on the materials to keep reduce the decoherence on this? So I sort of feel that that's in the works. That is, people are working on that. And again, I think you can tap into looking at the papers. There's a lot of experimental work in trying to build systems that have longer coherence times or a better fidelity for memories to do that. But yes, I think your question is how realistic it is. It's kind of realistic. Other questions?
Thanks.
Yeah, Steve, there's a quick one in the chat. First of all, thank you. When you swap and move forward, isn't it the qubit info that is moving forward? Or are we just establishing the circuit, so to say, setting things up for later when teleportation actually conveys the qubit info?
We're just creating bell pairs, but that's actually kind of an interesting comment, and that's come up, and I've asked them, why can't you just swap the qubits? Why am I doing the teleportation? And there's a couple of variants of this. Why don't I just swap the qubits hop by hop to do that? And the answer is that you have, as you move through the devices, you have to implement 2-qubit gates to make this happen. And they are very noisy, and things decohere really quickly as you 3 2-qubit operations, which is 3 CNOTs per swap to make this all work. So the idea here, so the idea here is that you may lose your fragile data qubit and not so necessarily your a bell pair. There's another protocol which is also similarly rejected, which is why not just do teleportation to each repeater? So that all I'm doing is a swap and a teleportation. And again, this gets into the number of swaps and the number of 2-qubit. See this sort of entanglement swap protocol rather than a hop-by-hop swap or a hop-by-hop teleportation. Other questions? Okay. So I think I've tried to convince you or talk to you about the fact that in order to make this all work here, we need to have distribute this entanglement. In particular, for doing teleportation and for eventually doing the swapping. So, and in particular, I've set up the entanglement as hop by hop. But what happens if I have multiple nodes in here? How do I manage the entanglement if I have not just point-to-point links, but a network, okay, or a grid of doing this? And so I just wanted to review here how this works. In our case here, we have our end systems in black and our repeaters in the middle here. And so what I'm doing is I'm doing an entanglement from an end system to a repeater, an entanglement between my repeaters, entanglement to my end system again, and then teleportation to the end to do that. Okay, so that's roughly the model that I've described to you. But, and again, it's all about this entanglement resources. That's okay. How do I reliably establish that? How do what's my strategy for doing this? When do I do it? How do I know that that entanglement I've created entanglement? Gone. And so here's our problems with entanglement. It's probabilistic. It can decohere and vanish silently. So if I have an entangled device, noise can destroy my entanglement. And how do I discover that I've lost this resource in here? It is resource dependent. That is, in order to make this work, I need to be able to store state. And whether it's quantum memory or however that's instantiated as spin atoms or however it's instantiated, I need some way to keep it around. Entanglement rates are slow in current technology based on the fact that it's probabilistic, so that you can't necessarily generate a lot of entanglement. And again, it decoheres over some period of time. There are devices in which you need to synchronize this. That is, if I'm going to provide entanglement between two systems that have quantum memory, I need to make sure that there's no entanglement. Memory. So how do I synchronize that classically to do that? And how do I manage the errors? Because it's possible that I have a path through a network, again, not hop to hop, but a path through a network. I may have one path that has less optical error than another, or there may be a repeater that is more susceptible to noise than another repeater. So how do I, as I create this entanglement swapping, how do I figure out what's the right path the right path. And so there are models for building entanglement, and there's a fantastic paper about entanglement that comes out of, I think, Delft, that talks about the issues of entanglement, the issues of link efficiency, and it's an hour paper unto itself. But it's a really great paper that sort of starts you thinking about how to model this, not just from an end system point of view, but any system. But ultimately, in a kind of a strange way, I'm doing this entanglement management, and it's kind of a routing problem. I have this set of this one-time bandwidth reservation that I was talking about before. How do I establish this? How do I make the right path based on errors? How do I figure out a topology to make this all work? And I'll come back to this because there's some interesting wrinkle about entanglement. And what's my strategy if I can create multiple entangled qubits in my network? What's my strategy for doing that, for establishing those and maintaining those? And I'll sort of provide more details. And how is this going to work if I have different types of repeaters and different types of end systems? Ultimately, in the middle, I have a photon that doesn't really know where it's coming from. How does that work with a different type of repeater other than an optical switch for a single photon detector device? And I have these synchronization protocols which are insanely complicated to make all these devices and all the entanglement work. Classic kind of engineering point of view. So as I said, that the question here is, can I create these graphs of entanglement in the background so rather than do this on demand and sort of create the entanglement as in my demo before, which I said, okay, we're going to do here, we're going to do entanglement, we're going to do swapping. Is it possible for me to create, or is an interesting strategy beyond on demand, is to keep entanglement paths floating around in the background? And that really, when I want to talk from one end to another, I simply find a graph of existing entanglement and essentially attach myself to that graph and do an entanglement swap with an existing graph of entanglement to do the destination. So rather than hop by hop, what happens in the background that sort of keeps this entanglement up and running? And the interesting part about that is I can have a process in the background that's constantly measuring the quality of the entanglement and creating this entangled graph, so that really all I need to do is find, as an end system, when it's time to do teleportation, I attach myself to this highly reliable pre-built entanglement to connect up with a destination. So how do I do this? What's the strategy for doing this? Is it on demand? Is it permanent? Do I do it hybrid? What happens if I lose entanglement in here? How do I run this background process for doing entanglement and kind of move out of the on-demand space? And so here's let me give you a couple of, I showed you the on-demand piece of this, which is simply as these repeaters and then do teleportation. But here's another example. Another example here is this partial background entanglement, which is in the background, I have quantum repeaters that are entangling independent of whether I need to transfer information or not. And so they're building like a partial graph of entanglement. And as time goes on, the entanglement happens between a bunch of different nodes. Finally, you have an end system to the network entanglement. Finally, you decide that you have a graph. Either it's end system initiated, which is create me a graph of entanglement here, and now I have a path from the upper left to the lower right, and I can now do entanglement swapping between all all I need to do is simply do my final entanglement swapping for my teleportation. So that's kind of one interesting approach. And the complications of this are, again, entanglement is probabilistic, entanglement decoheres silently. How do you track all this? How do you keep track of the errors that are happening? So, and we do teleportation. So there's another approach here, which is that rather than doing partial entanglement or lazy entanglement, I do continuous entanglement. That is, every repeater has an entangled path, and the network strives to maintain an entangled graph of all the systems here, so that when an end system is ready to do this, you have entanglement swaps all set up to make this all work. So that's another strategy. Finally, there's what we call spooky routing, and it's the observation that is basically that repeaters don't have to have adjacent entanglement. They can actually have entanglement that do entanglement swapping amongst themselves, such that you have entanglement paths that don't match sort of the physical links to make this all work, so that you can create these resources, these entangled resources in the background that aren't necessarily through adjacent repeaters. And so what you're going to do is build a directed graph or a graph out of the entanglement that doesn't necessarily map to the repeaters. So here's some examples of the repeaters establishing using the physical adjacency to assemble entanglement across many nodes here. And so in this particular case, you have entanglement that's not adjacent, but it is directed from the destination. So the end system in this particular case is already entangled with the first node, and that its sort of entry node, there's other entanglement floating around. And when it comes time to actually do the entanglement swapping, there's a background system, a classic system, that knows where these things are entangled, that can control how you do the swaps. You have an entanglement from the end system, and you can do teleportation to make that all work. So the entanglement sort of routing issues are interesting and complicated. You have, in order to pull that off, multiple qubits for quantum memory and pretty sophisticated control systems and error detection to figure that out. So, but these graphs are, as I said, they're transient. They silently decohere. Can I run entanglement detection protocols or entanglement error detection to figure out how to keep these entanglement resources up and running? Can I fix them if I find them broken? And what's an interesting approach for doing this? And arguably, and again, resource-driven, and arguably that, in fact, my strategies for doing entanglement routing that I showed are driven by what the types of protocols I can do and the types of techniques that I can do for entanglement error detection and correction. And so if I have poor techniques or I need a lot of entangled qubits for doing error management, it's possible that I have not a lot of options for doing some, for example, for the spooky routing techniques to do that. So one of the interesting things that's come up, actually, which was going to be presented at APS, which was, of course, canceled, was how do you figure out errors on links? And how do you figure out how fidelities for optical links, how do you figure out errors on beam splitters, how do you figure out errors on whatever technology you're running in repeaters? And Rod Van Meter, who is certainly one of the leaders in quantum networking, has come up with a link level tomography protocol for figuring out errors. So I talked about the fact that you are error correction and entanglement error detection and error correction. Somehow you have to have a technique for figuring out how this all works. So he has an interesting set of protocols that he was going to present at EPS for figuring out the errors inside of your quantum network. So again, we kind of beat this one to death, which is how do you distinguish between decoherence and classical link failure? And in fact, one of the classic routing folks, networking folks, asked me about this. Why can't I just use a source ACK to the source to destination to figure out whether the links failed? And the problem here is that if I do teleportation, if the entanglement is failed because of decoherence, how do I know that? What do I ACK? Because I have no idea what the data is that I'm getting. So even if I had a mechanism and in the middle of teleportation, the bell pair decohered, it potentially is random. And so I have no idea what to ACK, whether I got it or not, or what the value is, unless I run a higher level protocol or use a bunch of entangled pairs. So you need to, there's a lot of sophistication that needs to be put into these decoherence and error detection protocols to do that. And whatever you do, it has to be quantum mechanical, whatever protocols you come up with. It gets even trickier. You can start now doing a multipartite entanglement, and the protocols are interesting to do this, except we don't have a lot of qubits. Our largest machines are 53 qubits on the Google machine. So now if we're starting to use 3 or 4 qubit entanglement for teleportation, we run out of qubits really quickly to do that. So though you can generate protocols for doing the entanglement failure, you've run out of physical qubits to implement it correctly. So there is sort of some nifty things though, nifty protocols where you can build sort of this multipartite entanglement, these groups of qubits, in a particular type way in which if you have a graph of these that are error detecting, it's a very simple operation to join them together, to do the entanglement swap that retains sort of the error detection and the error protection capabilities. And that's sort of interesting protocols in the sense that you do have options on how you're going to set up this multi-partite entanglement in such a way that it makes it easy to merge these different graphs. So you have quantum repeater designs, as I talked about. There's quantum memories, which are just photonic beam splitters. You start getting to more the memory will support 2-bit gate operations. It's a quantum computer. And it's got some wrinkles about how you have to move things out of your quantum computer into photons. And here's some architectures. So someone did a survey of different architectures here. And I've sort of described the one on the upper left, which is repeaters with detectors in the middle. But there's other architectures where you implement the memory and repeat the devices inside of one computer. Send photons out. There's a variety of different optical techniques to do that for repeater architectures. And again, there's devices beyond just the beam splitter technology. Then there's more devices. If I have some interesting repeater architectures, can I in fact interconnect them together to build larger systems and larger switches? I talked about this. What I like is a quantum memory here. So I realize I'm, basically and trying to build this best effort entangled paths over this and supporting spooky routing is kind of what I feel works. And finally, how can I forget that as I deploy this entanglement, these graphs of entanglement, why not use a quantum algorithm to figure out the shortest path for my graph here? So not only can I use the entanglement here, I can write myself an algorithm to do shortest path first stuff calculations. So what's missing out of this? Well, more qubits, better transduction issues and faster rates, removing the optics out of this from the beam splitter technology, better correction codes and protocols, multipartite entanglement gives you a little bit more error protection, emerging standards so that all of us aren't inventing the same thing over and over in slightly different ways. How we build a classical control plane. All of these repeaters and end systems all need to be synchronized. What are the protocols and what are the standards for driving all that? And there's work being done in the IETF, which is the classics Internet Standards Group, on how to build some of these control plane issues. There's constant new techniques for repeater designs and new materials. I didn't even talk about security, okay? What happens if I hijack one of the repeaters here? What can I do? What can I learn? Can I find out valuable information about this? Are there interesting, better graph problems, different approaches for doing either on demand or spooky routing? Are there better protocols for doing that? And as Timur mentioned, it'd be really nice to have actual hardware to do this. And finally, someone pointed out that if entanglement is so valuable, why don't we trade it on the stock exchange so that you can simply buy an entangled pair somewhere for your own teleportation uses? So what do you know? It's pretty hard. There's lab-based systems that exist. They have a 30-kilometer implementation that they're doing. Again, I said that applications drive networks. Right now, we're just transporting qubits around. Are there other interesting applications, quantum applications, that will really drive quantum networking? What are they? What are the sensors? What are the end systems beyond crypto? It's hard. It's tricky and it's hard, and there's still a lot of work that needs to be done. And that's it. And I want to thank all my classic folks, the classical networking folks who kind of pushed me around on this. Dirk and Pri at Harvard, Dave Warren has also helped me out, Stephanie Warner from Dell, Matt from MIT, and my co-organizer at the Quantum Meetup. And at the bottom there is the Quantum Internet Research Group, and that is the engineering, sort of the standardization effort that's being done, and they meet pretty regularly, and they have some really good resources and work that they've done to sort of like figure out how to make quantum networking fit within the internet. Very serious group, and I have stacks of references and some really great stuff. Oh, and I sort of on the upper right, Rod Van Meter has a book on quantum networking, which I definitely borrowed freely from for doing that. And I suggest you follow him and have a look at the papers he's writing. He's certainly at the leading edge of all the quantum networking stuff. And there's a stack of references, and that's it for me.
Gosh, Steve, one of the observations I had, your busiest slide was work to do.
How about that?
My goodness. Personally, I'm flabbergasted. I was thinking we'd be talking about repeaters, but you've taken my curiosity to a whole nother level. I mean, it's almost like back in the early 80s, designing the ARPANET. I mean, that's child's play compared to, this notion of entanglement management and routing, and holy cow.
I gotta tell you that the thing that my classical guys stumbled over was the idea of this no cloning problem. And if suddenly you can't copy a qubit, your engineering options completely change in what you can do. And I think that's a lot of this has to do with that, and the fact that what can you do to transport this is a lot driven by no cloning. And it took me a while to explain them because they were like, sure, you can copy anything. Like, cannot copy a qubit to do that. There is a lot of work that's being done. There's a lot of engineering work, the materials work. There is a lot of interesting, one other interesting observation is that there's many protocols and a lot of work that's being done in, for example, for noise models and error correction and optimal gate operations within a quantum computer. Those are all so there's a lot of work that's being done that's easily translatable into networking, into the networking things, other than the fact that the hardware is just way behind computers, etc., because of this sort of dissimilar systems and this transduction to do that. But a lot of the protocols and the theory is kind of, pretty up to date.
I'd say too that it presents a whole lot of work to do that many of us, that is reachable for many of us. You don't physically need routers, et cetera, to get involved in the network design and so on. I've got a couple questions here.
Sure.
What would be the IPv4, IPv6 equivalent in quantum networks to identify these quantum repeaters, not the network?
So feel free to unmute yourself to make sure that I understand your question. I think you're asking.
Hey Steve, yes, this is Amalak. Basically, to identify these devices on the networks, what kind of addressing would be used?
I was thinking the same thing. Like the IP protocol, for example.
So there's all of these devices need classical system control systems to do that. So they all will end up with IPv4, v6 addresses for these to address these individual sort of routers. However, how you define and so you can figure out sort of what an address is and how to do the control systems do that. What I find really interesting is how do you identify a multi-hop entangled path? What's that? Is it like a virtual link or what is it? So there are some tricky things that don't really map well into the existing IPv4 and v6 world. Doing entangling things and then I'm changing the entanglement around or doing entanglement swapping. Somehow I have to keep track of that. And addressing IPv4, IPv6 endpoints for entanglement feels like the right thing to do, but I'm not sure to do that. But again, all these repeaters they all have to have classical IP addresses because they all need the control plane to make that work. Does that make sense?
Yep, thanks.
So one thing I wonder about is, are we constrained by our old way of thinking? Might there be different ways to think about the problem down the road? Anyway, got another question. I thought there was a QKD path near New York City for Wall Street use and also one between China and Austria. Are those just proof of concept sort of things, research labs?
So QKD it's an interesting protocol, and the short answer is yes, there are. There are there's a couple of types of QKD protocols. There's BB84, and I'm doing this from memory, and the Eckhart protocol. BB84 is a protocol for determining secret keys without an intermediary, and what's possibly being eavesdropped. That just requires a path of photons with certain polarizations to make that all work. It is quantum in the sense that if you eavesdrop it and you look at it, you will change the measurement and it will do the same thing. Those aren't proof of concept. You can buy devices. will do QKD. It is an interesting application, but it feels, and you can certainly do it on, run the, certainly the Eckert protocol on top of this. I don't use it as an example only in the sense that it feels like it's a solved problem. And I'm much more interested in applications that don't have solutions right now to do that. And it's, I think I briefly cruised through, mentioned those protocols in the beginning as applications, but they work and they're commercially available. And in fact, I believe that there's an article, a discussion from maybe a year or two ago about the Chinese who used free space photon transmission and entanglement for doing QKD distribution, for doing key distribution off the satellite. And they got that to work. So I think there's just more interesting applications out there. I don't know what they are, but they're more interesting.
It's for us to invent. Okay, one more last question here, Steve. It's a question on workforce, which is what I'm passionate about. Given you are from networking, how does the quantum networking team look to him? Is it composed of physicists, network engineers to maintain quantum repeaters and quantum networks? What's the workforce look like?
Interesting question in the sense that there is, there is sort of this problem, sort of bootstrapping problem, which is building these devices and, connecting them to optical links and getting back to the example I average to Harvard MIT to Harvard to out to Lincoln Labs. We need boxes to make that all work. So certainly the workforce starts out in how do you build a box to do this? And that is, right now that's a materials problem. It's not an engineering problem. I wish it was an engineering problem. I wish I could buy transduction devices to assemble that. But that's building, having physicists and materials people, real-time engineers for doing synchronization for control system engineers to put this all together. Right now, to build the boxes is where that starts. As it gets deployed, once you get the boxes on there, you have the people that are going to build favorite earthquake and magnetometer example. Somewhere someone's going to have to install magnetometer sensors on a fault line. How does that get run? How are the optical links connected from those sensors back to something that can do more analysis to do that? So, in that particular case, it's not, the workforce is both the deployment and management of those particular devices to make that. And finally, there's the whole point of this is to be able, all I've done is transport a qubit. I haven't actually written or run any processing on these qubits. So I need programmers that are going to take, all these teleported qubits in here and do, run sort of the classic algorithms on this, perhaps Grover search on looking for a value or quantum example of our earthquake or a seismic change. So there's the other piece of this is there's programmers that are still required here to be able to do that. So that's kind of like and people writing algorithms like that can start today. Those algorithms are still going to be useful to do that. So that's kind of my survey of the workforce.
That was the last question, Steve, but there's one more here, and it's kind of entangled with the prior question.
Oh.
So it's still the same question, right?
It's the joke that keeps on giving.
Oh, sorry. I'm new to this. I haven't used them all yet. Just quickly, and then we'll cut you off or end it after this. Currently, are there any methods or processes for smooth transitioning from classical to quantum networks? Or is that even a thing?
The short answer is no. The quantum world is distinctly different from the classical world, and there is, what exists in the quantum space is just, doesn't really match well with the sort of the micro quantum world doesn't match well with the macro world here, and so it's just the moving from that one space to another is hard, and I think that's the this what's missing and what's the future slide is pretty much addresses that. That said, there are many control systems. There's so much IP work out there on building control systems, distributed control systems that can be adapted for running these particular protocols. There's very precise timing protocols out there for doing this. There's a variety of techniques that we've developed over the decades for running distributed control systems that we can use for quantum. But once we escape into the quantum space, or once we drift or move over into the quantum space, then I think things get tricky. Things are hard and different and need to be thought about differently.
Okay, I think we better wrap it up there. We're on overtime here, Steve. Thank you very much. Hey, I just noticed, folks, there's a reactions button down at the bottom of your Zoom screen, so go ahead and give a thumbs up or a clap. I don't know how that works, but yes, we definitely want to invite you back, Steve.
Thanks for the feedback. Invite me back on that, and I think it'd be interesting to sort of, for me, to play this forward in a year to see what's changed, to talk about the new technology.
All right, we'll add you to the calendar.
Thanks for the invite, folks. I really appreciate it, and have a nice night.
You too. Good night, everybody. Thanks for listening, and we'll see you next time. Thanks again, Steve. Bye.